Okay, let's just now continue with from the previous part where we have the Bn here, okay, and the Bn can be found from this equation where the Ft need to multiply with the sine and omega t, okay, and from here we can solve the integral and we get the value of the Bn. At the moment, okay, I will only concentrate on the steps on how you can identify all the important values, okay, for solving the Fourier series expansion first. Alright, now after knowing all the A0, An and Bn, then we can plug in all the information into the general equations of the Fourier series expansion as what you can see in the equation 1. Okay, so by knowing that Ft equals to this, okay, and we know that the A0 before this is 1, so we can say that we have the first term, and this is called as the average value, okay, where the function, where the value of where this value has no frequency, or the omega equals to 0. For the next terms, okay, where we can see that in the previous, the An equals to 0, so you can see that here we don't have, okay, any summation that multiplied with the cosine, okay, so it means in this case we have no An values, okay, I mean the An which is starts from 1 until infinite. So we don't have this one. It means this value 0. Here we know that the A0 is 1, then we have this, and then plus with the summation of Bn sine and omega t. In this case we know that the Bn equals to 0 for even n and 2 over n pi for odd n. So I can now write it like this, okay, where I have a summation of all the Bn sine and omega t, but only for odd n, okay, because the even n gives me all the values of 0, okay. So what you can see here, this is the Bn, sorry, this is the Bn that we found before, okay, and this is the sine omega t. So n omega, the omega is pi over 2t. So from here actually reflects to this one. Alright, so in the end, this is the final value that we have, or final representation of the Ft, okay, for the function of this periodic function. Alright, you can see that from this slide, okay, it can also be represented like this, okay, where we can now replace all the value of n start from 1. So we have sine half pi t, where we have 2 over pi sine pi over 2t, so we got 1. And when n equals to 3, we don't have n equals to 2 because it is only defined for n odd n. So when n equals to 3, we have 2 over 3 pi sine 3 over 2 pi t, okay, so on and so forth. Okay, so this can also be simplified into this, okay, where we have all the value here represent, okay, for all the odd number, and this is also represent also the odd number. Okay, so either one of these answers, okay, can be accepted as the final answer for the Ft. Alright, so now let's go to the second example, where in this example the function that we have here has a period of t equals to 2 pi. So automatically the omega equals to 1. Alright, then we can use equation from the series from the equation 2. So here, when the t equals to 2 pi, omega equals to 1. Now, obtain the Fourier series expansion of the periodic function of period 2 pi defined by this equation. So this equation gives us ft equals to t when the t defined from 0 to 2 pi. Okay, and the ft equals to ft plus 2 pi. It means now the period is 2 pi. Alright, so knowing this equation, we can sketch this function like this graph, where from the first definition here, I can only define it from 0 to 2 pi, and the function of the ft is t. It means here the value is 2 pi. Okay, so by knowing this, okay, I can only sketch this. But if I know ft equals to ft plus 2 pi, it will allow me to repeat the same pattern to the rest of the graph with the same t. Okay, so if this t equals to 2 pi, so in order to have t equals to 2 pi here, then I should have 4 pi, okay, at the end of this point. Okay, so this is how we sketch the graph. But if we want to obtain the Fourier series expansion, first identify the t equals to 2 pi, omega equals to 1, then use series 2 because we know that the t equals to 2 pi, and after that identify the ft and the boundary. In this case, the ft is t and the boundary starts from 0 to 2 pi, okay, from this equation. Next, after we know that, the same process happen, okay, where we can find the value of the an here, and we know that the 2 over t is 2 over 2 pi, which is 1 over pi, and the boundary is from 0 to 2 pi. Here we can straight away use the whole boundary because we only have one function share, okay, one function only, which is t. Okay, so by knowing this, then we can then solve the integral and we get the a naught. The same process for the an, okay, multiply the ft with the cos and t. Okay, why you don't see any value of omega here? Okay, the omega here has the value, but the value is 1. Alright, and after that, solve this an and you get the value, which is 0 in this case. Okay, it looks like simple from this slide, but you need to work out yourself on how you can get the an here, okay, by using your understanding or your skill of the integral. Okay, next, of course, we want to find the bn. Okay, so the bn is the multiplication of 1 over pi, okay, with the integral of ft sine and omega t, or sine and t here. Okay, and from here we get the bn, okay, and this is the final output after we did the integral. Alright, now it not ends like that. Okay, after we have found all the all the a naught, an and bn, then we will put all these values into this equation. Okay, so once we know the a naught, so this is the value of the a naught over 2 just now. Since we have a naught equals to 2 pi, so 2 pi over 2 becomes pi. Okay, and here we have an equals to 0, so we don't have any value here, so it means here I have 1 over 2 pi, here the value is 0, and here depending on the value of the bn that we have, okay, in previous. So at the end, this is the final output that we have for a representation of periodic function using Fourier series expansion. Okay, so that's all for this part 1 of the Fourier series.